Welcome to this 7-minute video on limits relating to Leaving Cert Higher Level Maths. Strand 3 says we need to recognize these two limits by inspection. If we consider the first of these, the limit as n goes to infinity of n over n plus 1, well, we can rewrite this by dividing above and below each part of it by n. When we do this, the limit turns into the limit as n goes to infinity of 1 over 1 plus 1 over n. Now this 1 over n, let's consider the value of this as n goes to infinity. So what is the value of 1 over infinity, or 1 over a very huge number? And this is going to be something very small. 1 divided by something very big is going to be something very small, or approach 0. So the answer to the limit is 1 over 1 plus 0, which is just 1 over 1, which is 1. So we could learn this result. But rather than do that, we could also do it in a less formal way, because it's just by inspection. We could use a calculator to approximate this. So for instance, if in a calculator, we can't put in the number infinity, but if we put in a very large number and divide that by a very large number plus 1, what would the value of it be? Example, just even reasonably large number, say 999 divided by 999 plus 1. Well, 999 divided by 1000 is 0.999. And you can see on the calculator, this approaches the value 1. And this is sufficient for Leaving Cert, that you could work this out. Let's now consider the second of those limits. The limit as n goes to infinity of r to the power of n, where the value of r is a number less than 1. So it could be plus or minus, but it's a number between -1 and 1. So it's a small in magnitude, this number. If you imagine, for instance, if r was a half, just because it's an informal way we'd look at this. So if you imagine the limit as n goes to infinity of a half to the power of n. So like, what would a half to the power of infinity be? Or a half to the power of a very large number? Well, this would be the same thing as 1 over 2 to the power of n, since 1 to the power of n is just 1. So what's the value of 2 to the power of n? Well, 2 to the power of something very large would mean it's 2 by 2 by 2, close to an infinite number of times. And this is obviously going to approach something very, very large, or approach infinity. So what would the value of 1 divided by this very large number? Well, this would be like 1 divided by infinity, almost. And this would have to be equal to 0. It's something very small, or 0. So the limit of n goes to infinity r to the power of n is equal to 0. Now we could imagine this a bit simpler, even like the half one. Suppose you had a cake and you half it, and then you could half that cake again, and you half that cake again. And if you keep halving it, it's fairly obvious that you're going to be left with something very small, that it approaches something almost equal to 0 if you halve it enough times. Now we use this result, this last one, to use a proof that is on the course, to prove the sum of an infinite geometric series. Now we're given in the log tables the sum of a geometric series is given by this formula, and we want to prove, again given the log tables, that the sum to infinity of a series is equal to a over 1 minus r if r has the size less than 1. Now we're going to use this result from last. Remember that the limit of r to the power of n is equal to 0. So what's going to happen this time, instead of putting r to the power of n, r to the power of infinity approaches 0. So we're just subbing that in for 0, and that proves that formula. It's a very simple proof. Okay, now let's consider the idea of continuous or discontinuous. Now this relates to limits as well. So the continuity or discontinuity of functions. Now it's not a formal proof, but to know if something is continuous or discontinuous, you ask the question, do you have to lift your pen to draw the function? If you do, it will be discontinuous. For instance, a straight line y equals mx plus c is continuous, or a cubic function is continuous. You don't have to lift the pen. But this rational function is discontinuous. You'd have to lift the pen, or this simple function here is discontinuous, you would have to lift the pen to draw it. Now this here is an example of a discontinuous function. It's a rational function. Y is equal to minus 2x over x plus 3. We can see looking at it that it has both vertical and horizontal asymptotes. Now supposing you didn't know what these were, we could use limits to decide what these were approaching. Let's consider first, we'll just draw these asymptotes first. So there's the vertical asymptote. Now we can see its value from this graph here at minus 3, and we can see the horizontal one has a value at minus 2. But supposing we didn't know this, how could we find it out? Now we could see that you cannot divide this function by 0, and that would happen when x has the value minus 3. So let's consider the limit of the function as x goes to minus 3. Now to do this, we imagine approaching the minus 3 from the left hand side, so a number a little bit smaller than minus 3, for instance minus 3.001. If you sub that into the calculator for the values into the function, what kind of value would you get? Even if we didn't have a picture of the function, we'd see that it approaches a number over 60,000 or minus 60,000. It's a large magnitude, a very negative number. If we approach it from the right hand side, pick a number a little bit bigger than minus 3, for instance minus 2.99, and stick it into the calculator, we see we get a very large number. So we imagine it must be going towards infinity. This proves the function is discontinuous as well, if you approach from different sides and it's not approaching the same number. If we put in a very small number for x, we see y approaches minus 2. A very large number for x, we see y approaches minus 2. And this tells us how to work out the horizontal asymptote. So if you understood just this diagram, it's probably enough on functions and discontinuity.